Morning, sir.
Good morning.
Good morning, sir.
Yeah, morning. Yeah, thank you. Okay. Okay, let's start the class. So before that, I just want to check. So any questions so far? So today is the 2 hours lecture, right? So most probably by today we'll try to complete this one related to this processor. So today we are going to discuss about these hazards, data hazards, and control hazards, and finally we'll see the exceptions, are also known to be interrupts and all. So we'll see that how to deal with them while designing the data path or controller and all. Right. So so let me share the slides. Yeah, and please keep your mics in mute, right? So last class actually somebody we have just so please make sure that your mics are in mute. Okay. So so can you see this slide? Hello, the data hazards in ALU instructions. Hello.
Yes, sir.
Yes, sir,
Yeah.
it is visible.
Yeah, good. So, so if you recollect in the last class, actually we just focused on the design of data path and how the controller will be in case of pipeline architecture. So these two aspects we discussed in the last class. And today we'll see that we're already aware of that there are certain issues while executing the instructions for a pipeline. There are known to be hazards like data hazards, control hazards, and structural hazards. And we are aware of that, what they mean, and then why they arise and all. So we'll try to see that in today's lecture. We'll see that how to overcome that, or we'll try to see some possible solutions to handle these hazards, particularly data hazards and control hazards. So we know that the data hazards means actually when the instructions are executing, or in case of sequence of instructions, if there is a dependency between the successive instructions, then we have the inconsistency in the data handled by the instructions that will arise and all. So they are known to be the data hazards. So here, if you look at the sequence of these instructions, and here first we'll try to focus on data hazards in case of while when you are executing the ALU instructions, and later we'll see that the data hazards due to the load also. And here you can see that all these instructions, the sequence of instructions are the ALU instructions, like that is arithmetic and logical operations. The instructions that are performed will be arithmetical or logical operations. And if you look at here, the first instruction is the subtraction. The result of the subtraction will be used by the following instructions like AND, OR, ADD, and so on. Because the result is stored in the register number 2, and it is required by the AND operation, then OR operation as the register arguments, as the register operands in the following instructions and all, right? And it arises the hazards and all, because here the subtraction instruction will store the result into the 2 in the write back stage, but here the following instruction requires that data in this execution stage itself. So if you look at the sequence of data paths with the time aligned, then you will come to know about where these hazards will occur and all. So here the issue is that actually how do we identify these hazards? How do we detect these hazards first? And then suppose after detect the hazards, if there is a possibility of forwarding the data, then we can perform that forwarding the data can be performed so that the pipeline will not be stalled. So we'll see that if you look at this particular diagram, they say here the data paths are arranged in a time aligned fashion. These are the if you look at these are the sequence of instructions, just whatever we have shown earlier, and this is the timeline, that is clock cycle 1 and so on. It progressives, and initially assuming that the register 2 contains the value 10, and this arithmetic operation, that is subtraction operation, will change this value to minus 20, and the change takes place only in the clock cycle 5, only in a clock cycle 5. But the following instruction operates on that value, the changed value minus 20, in the following instruction, that is, and the operation will be performed on this register data. But the register data will be available, the proper register data will be available in a clock cycle 6, actually in a clock cycle 6, because in a clock cycle 5 the register data the data will be right into that one, but in a clock cycle 6 in the execution stage it is available. So but here in the AND instruction we need to perform the execution in a clock cycle 4 itself. So for that there is a problem, because here by this time the register file doesn't contain the data, so we have an issue, data hazard. And likewise in the next instruction, that is R instruction, here also here at the clock cycle 5 it requires the execution, where that execution requires operand from the register 2, but still the register 2 is not available in the register file, right? So again here also we have a hazard, you have the hazard here. So then the following instructions, even though they have the add and other instructions, so they don't have any hazard, because the following the add instruction, so it requires execution in the clock cycle 6, right? So by that time already that value is updated, so no issue at all. Then the following instruction, no issue. Here for these two instructions, you have the data hazard. So you can avoid this data hazard, or you can one way is that actually to overcome this, one way is that you can stall the pipeline. You can stall the pipeline. That means you just generate the no operation in the corresponding execution stage, so that till the data is available, right? So that is one solution, just simply stalling the pipeline without moving. And so with that, actually here the instructions execution time will be delayed, so that affects the performance and all. So the other way is that actually you can able to forward the data if it is possible. So here in this case, both the cases where the data forwarding is possible, right? Because already here the required data for this AND instruction is already available here in this pipeline. It's there already, because that is already executed. The result is placed in this pipeline register, but it takes another 2 cycles to place it into the proper register. But here the register is the data is available. And anyway, the following stage requires this execution. So therefore, you can take the data, you can tap the data from this, right? And similarly here also for the next instruction also, or also here by this time here this requires the execution, but the data is not available. But still the data is available in the memory stage, So you can tap that. So that way the forwarding is possible in both the cases and all. So here the thing is that how do we identify that? How do you identify that if where is the data hazard, and if the forwarding is possible or not? So how do you check that one? So here in these two cases and all, there is a data hazard, because the operands request from the register file, but the register file doesn't contains the desired value and all, right? And so that's a hazard. And here the possibility of forwarding is possible. Like in both the cases, the pipeline need not be stalled. So if we have a proper hardware circuit to forward the data from its pipeline registers appropriately, then the pipeline will not be stalled, and it will be continued. So the thing is that how do we detect this hazard, data hazard, and then how do we forward it? So for that, here we'll make use of some circuitry or some controller where it will detect the hazards, and then it will suggest the forwarding values from the appropriate pipeline registers and all. So now we'll see here like how do we detect the hazard. So here the hazards can be detected. For example, here if you look at here in this stage here, here for example in between these two registers like subtract instruction and then following these the like add and instruction and all, right? So here in this case, if you see that in case of and instruction here, that means here at this point of time, you need the register operand from this pipeline register. That is, this pipeline register corresponds to ID and EX because it has to pass the data to EX stage. So therefore, this pipeline is ID EX register. So from this ID EX register, it has to fetch the register contents from this register contents. So if we know that actually here, whatever the register contents it is fetching, right, from for this particular stage of this and instruction, and if it is equal to these register numbers are equal to, so whatever the contents here by the previous instruction to be written into a particular register, if these two registers are same, so it means that whatever this earlier instruction where the result is calculated and it has to be placed into a register file, and that register number whichever is to be placed into the register file by the previous instruction, if that register number is same as the register number of the following instruction which is required for its execution, if both are same, then you can say that there is a hazard. There is hazard because here, because the register numbers we know that, but the value is not placed in the register. That's why you have a hazard. So therefore, if you can able to come to know that, if you can able to verify that the registers that are the contents of registers that are required here in the execution stage of this instruction, and the contents of the register, the values that are there available here after execution, which are need to be written into a register, if this register and this register both are same, then you can say that there is a hazard is there, and then you can able to handle the hazard by using forwarding. The same way here also, you can see here in this case also, where here the execution stage requires the register operands, right? But those register operands are not available. But the values that are needed to be written into the register, they are available at this stage at the memory and write back stage and all. So at that time, so if you can able to verify the register, the values where to be written here and the values from where had to be fetched here, if the both registers are equal, then we can say that here there is a hazard at the at this point, like at this point. So we can able to handle that by forwarding the data directly from the output of a memory or like from this pipeline register and all. So now here that how to check that for checking that one here we are using a convention that like the register names we are convinced we are using that RS because we know that in the case of arithmetic instructions it contains the three registers RS, RT and RD, where RS and RT are the source operands and RD is the destination operand. That means where the result has to be placed over there. So here the in case of to perform execution arithmetic operation execution, the register operands are either RS or RT, either RS or RT. And this RS can be available from the pipeline register IDEX, IDEX, because it is in the border between the instruction decoding and execution. So in that register, the required register values, that is the contents of register, they are available and all. So that way here these register names are like here that the terminology will be like that. In case of if you want to check the register numbers at the EX stage, that will be ID/EX dot register RS. It means that it's one of the operand. Likewise, the other operand IDEX dot register RT, that is the second operand. So these are the two operands where upon which the accumulator or the arithmetic logic unit will perform the arithmetic or logical operations and all. And now we need to check that the data hazards will happen in these cases. You can see one among these cases. You look at here. So the IDEX register dot register RS or IDEX dot register RT, whatever. So these two are the register operands that are required for execution in the third stage. And the following stages here in the at the beginning of a fourth stage where the result is available from the previous instruction, either the beginning of the fourth stage or beginning of the fifth stage where the result is available, but still the result is not written in the RD register, but the result is available at the end of the third stage and at the end of the fourth stage and all. So now if you can able to check that the register operands that are required for execution, if they are same as the values that need to be written into the register RD, if the registers are same, register identities are same, then say that the hazard happens. There is a hazard and all. There is a hazard, and where we can able to handle this hazard by forwarding and all. By forwarding. Suppose if these in these two conditions, for example, one of these, because the destination register, if it is equals to one of these operands, then the you can say that the hazard is happened here. That is between between the just the previous instruction and the next between the two consecutive instructions and all, right? And suppose if this hazard happens, if this condition satisfies, it means that there is a hazard between the instruction between the two instructions which are separated by one more instruction, right? Because here you see that the other instruction is at the memory write back stage, and the current instruction is in the IDEX stage. So therefore, there is one more instruction between that ID memory stage was there. So therefore, here in this case, the instructions are separated by one instruction. Here, these two are the successive instructions. So if you in these cases, if the register operands that are required for execution stage, if there happens to be like the register operands that is meant for destination, so in that case you have a hazard and all. So this way you can able to, at least this is very at the register level identities, by knowing that one can able to detect the hazards and all, right? And then afterwards we'll see what is the further is required. This is one primary requirement where the previous instructions their results are calculated and results are not placed in the register, destination register, and we know that where to place and all. And if somehow if you can know that actually that the destination register name or destination register number, if it is same as the register operands or register numbers that are required for execution stage, then in that case we have a conflict. Then in this case we can say that there is a hazard and all. So that you can able to solve it by using forwarding. So this is the one very primary condition that is required to check that whether the hazard is there or not, to detect the data hazard and all, right? And after that there are even though the register contains matches and all, there are some instructions which they don't really write into the register and all. So to ensure that, but here what we require, because the execution stage will supposed to fetch the content from the registers, right? And if the instructions are not writing into the register, then in that case the forwarding cannot happen and all. So therefore here we need to ensure that along with the matching the register names and all, we also have to ensure that the previous instructions should write into that particular destination register, should write into the particular destination. How do we ensure that? So for that, we know that actually if you want to write into the register file, there will be a control signal. So that will be active. That will be active. But that control signal will be generated in the respective instructions during that stage 2 itself. But they will be propagated through the various stages, and also you can tap them and you can able to come to know that whether the previous instructions they really write into the register or not. So that way you can able to check that actually here the EX memory stage register write and the memory write back register write. If both are same, if both are like non-zero, it means that the desired instructions, the previous instructions, they will write into the register which are required by the execution instruction and all. So that way this has to be ensured. That means this is to just check that whether the instruction is really right into the register or not. And one more thing is that whether the destination register is supposed to be not a zero register and all. If the destination register is a zero register, then what happens if you try to forward it? The value that may be generated may be different, because finally when you are putting the value into the destination register, if there is any other register, no problem. That is whatever the value you are storing, that will be retained there. But if the destination register happens to be zero register, for example, in that case, whatever you put it, whatever you try to place it into the zero register, but the zero register will reflect only the zero value that we know that. So therefore, again, we have to ensure that the destination register should not be zero value, zero register. So these are the like some of the constraints that need to be imposed with over these basic conditions and all, these basic detection constraints and all, conditions and all. So this is the basic one where the current instruction or the register operands, whatever is required. So they are those operands will be given by the previous instructions and all. So for that we are now checking the register identities and all. Then after that again the further things we are just checking that whether the instruction is really writing into the register. For that by using these control signals you can able to check it out. And then whether the destination register is a non-zero register or not. So that also we are checking here. So by placing all these things together, the conditions will be like this. By placing all of them put together, the hazards will be like that. They can able to make the condition like this. You can say that if the EX memory register write, that is, it is means it is set, it is asserted, and EX memory register RD is not equals to 0, it's not a 0 register. These are the two conditions that that are on top of the basic condition. This one EX memory register RD equals to ID EX register RS or RT. RT. It means that at the just this condition is that between the two instructions that are successive, that is one in the execution stage and other will be just passed out the execution stage. So in that condition, in that case, by using this condition, you can able to check it out, right? And sometimes no, it can happen that the instruction will be there in the memory write stage and all. So at that time to check that whether to forward it or not. So at that time you can make use of this particular condition will be useful and all. We have seen both the cases in the previous sequence of instructions. For the immediate instruction we request this one, we will make use of this one. But the following instruction, that is the next to next instruction, we will make use of this one. Will make use of this condition for forwarding the result and all, right? So this is nothing but just whatever we discussed previously, just clubbing all the conditions together. So these are the like conditions or the rules for checking the hazard and as well as forwarding the paths, forwarding the values also. And you can see here, this is the circuit where you can see that this is the forwarding circuit, and here the forwarding circuit will be placed in the execution stage of the instruction and all. So for this forwarding circuit, what are the inputs that are required? The RS and RT of the current instruction from the IDEX register, RS and RT, right? You can see the forwarding unit there. These are the two inputs, either RS and RT, and the EX memory. That is, these are the two destination possibilities. One is from the soon after the EX stage, and other is after the memory stage. So these are the RD registers. So here these will be compared. These are compared. This is a simple basic forwarding circuit without imposing the other things. Like if you impose other ones where that requires that you have to check that whether the control signal corresponds to EX memory write bar is 1 and memory write bar is 1. So that is there. That was included here in the later, and I will show you. So the forwarding unit, it requires the inputs from these inputs, which are indicated by black arrows and all. And from these inputs, it will just check the condition, and if the conditions are satisfied, then it will ensure the forwarding. It will ensure the forwarding. You can see here the ALU here input. You can see that there are two multiplexers here. So here without this forwarding circuit, the multiplexers have only two inputs. The multiplexers have only two inputs. So one is that for the top multiplexer, the inputs will be, one is from the register operand directly. What is the other one? The other one is from the register operand is one of them. And here the other inputs are like, one is from the there is a possibility of forwarding from the output of EX stage, that is one input, and the other possibility is that output of the memory stage and all. So there are two inputs from regarding the forwarding, and this is the original one. Suppose if already data is available in the register and all proper data, then this will be enabled. Otherwise, if the data is not available here and you require the forwarding data, so in that case, there are the two possibilities and all. So you need to here this multiplexer, there are three inputs are there. Out of that, one has to be picked up. either the register operands directly or the forwarded values. And again, these forward values, also whichever the forward value has to be can be allowed, like from the output of the execution stage or output of the memory stage and all. So for that, based on the hazard, whichever, if it is hazard at the here as the execution stage happens, then you need to forward immediately the soon after the execution stage. Otherwise, if the data is available here, you have to forward the data from the output of a memory and all. So therefore, here the forwarding circuit job is that it has to provide the control signals to these two multiplexers and all. So if there is no not if there is no forwarding is required, then only the desired register contents will be like passing to the ALU. If the forwarding is required, then based on the logic, it will forward appropriate the input either from the output of execution stage or the output of the memory stage and all. Right. So yeah, right. You will see that actually if you look at this thing. So this is the actual forwarding circuit. We'll see that here in this forwarding circuit, you can see that instead of these 4 black arrows, there are two blue arrows also there. These 2 blue arrows corresponds to the writing, whether the instruction is writing or not. That means that the write back after the execution stage and the write back control signal after the memory stage and all. So this is the actual one, and then you can see here. Yeah. Yeah, that is what. Yeah, yeah, correct. Right. So yeah, it's clear, no? Right now. Now here, this is the forwarding circuit. The black arrows corresponds to just they provide the register identities from the IDEX stage and from the destination registers from the end of the after the execution stage, after the memory stage and all. So this comparison will be takes place, and along with that, we also have to ensure that the following is the previous instructions should write into the registers. So these are the two control signals for that. And also internally that also we have to check that the register address should not be 0. The register address, the destination register should not be 0. That also has to be checked. Then it will appropriately forward, like whether to consider the output from the directory register contents or one of these two forwarding, inputs and all. One of these two forwarded inputs, right? So this is the data path for the forwarding circuitry in case of the data hazards, right? Yeah, right. Here there is one a problem here in the data hazards. Like there may be cases that actually if you have these two forwards data hazard, memory hazard, here most of the cases actually one of these two will be true. Like if you look at here the previous example, like here if you look at here, when this instruction is executing at that time in this execution stage, here when you check the both memory hazard and the data hazard, sorry, when you check the ex hazard or the memory hazard, that means when you check with the like for the outcome of this pipeline and the outcome of this pipeline with respect to this particular pipeline, then only this will satisfy. This particular one will satisfy, right? So because of that, then we'll forward this particular one. And similarly, for when this instruction is the execution stage, again the forwarding circuit will just check the two conditions, whether this will satisfy or whether the immediate one will satisfy, whether this can satisfy, whether this is satisfied. Out of this here, only this one will be satisfied. So therefore, the forwarding path from the after the memory will be forwarded here and all. So that way, most of the times here the forwarding, even though we check the both the conditions like after the execution stage, after the memory stage and our pipeline register, but only one of them will be satisfied. But there are occasions where if the program is or the code is something like this, for example, if the code is something like this, it means that here just we are adding the like a sequence of values, for example, we are adding the a sequence of array values and then placing the result in the same register and all, placing the result in the same register. Like for example, you have 1 and 2 or contents of 1 and 2 are added, place it into 1. And then the content of 3 is added to 1 and again place it into 1. And the content 4 is added to 1 and then place it into 1. So likewise, always the result is stored in the same register and that is also used as a source operand, for example. So in that case, if you execute if you try to execute these three instructions in sequence, right? So when you come to the third instruction execution, when you come to the third instruction execution stage, when both hazards will occur, both hazards means both will happen. Like for example, at the end of execution stage, the previous instruction will result, this condition will be satisfied, and then again the previous to previous instruction here, this also will satisfy, because here also till the actual result is not placed into the destination register and all, right? Still it is there in the at the output of memory stage and all, right? So therefore both these instructions, previous instructions will satisfy for this particular execution of this instruction, the third instruction and all, right? It means that what I mean to say is that both here the previous you are checking the conditions either for EX hazard or memory hazard. EX hazard means just tapping the output from the end of the execution stage to the current execution, and a memory hazard means tapping the output from the end of the memory, like memory stage, to the execution stage. So we are checking these two conditions. Most of the cases only one of these two conditions will be satisfied. So with that we'll pass the appropriate, we'll forward the appropriate value. But here in this case, in this scenario, the both conditions will be satisfied. Both will satisfy, because if you look at here the kind of instructions here, you can see both of them in both the cases and all, the destination register is same. Both the cases the destination register is same. So here in this case, but the latest value to be considered by the third instruction will be just its previous instruction. Just it's a previous instruction, because here the previous instruction already taken the destination of this one, and then it computes it executes, and again its destination is also there, but both of them, they are still not written the data into its corresponding destination. Both of them are in the intermediate stage, are in the stages where they are not written actual value and all, but both of them contain the intermediate values and all. So therefore here when you are executing the third one, it requires the most recent one. So that means the value that is computed by the second add has to be placed over here, has to be forwarded over here. So therefore here if both hazards occur, then we need to use the most recent one. So therefore when you are designing the forwarding circuit, you need to also include this constraint also. This constraint, that means if both constraints are satisfying, so at that time you need to take care about only the recent one, that is the value that is at the end of the execution stage has to be considered. So therefore by revising that condition for the memory hazard, you can say that when the memory hazard has to be activated, at that time you need to check that the execution hazard should not take place. If the execution hazard is not taking place and only memory hazard takes place, at that time you tap the value or you take the value from the output of memory and forward it. Otherwise, you had to forward. If both are satisfying, then at that time the memory hazard will not be considered. The memory hazard will not be considered. It means that you forward the value from the end of the execution stage of the just preceding instruction and all. So that way, this is further refined the forwarding circuitry and all. So that way here, this is the final forwarding circuit for for detecting the hazard, as well as for forwarding the appropriate outputs from the execution stage or from the memory stage and all, right? So you can see here the inputs that are coming from here, and then yeah. Yeah, still, even though we have we have designed some forwarding circuit where it can avoid the stalls for certain cases and all, but still there are certain cases where if the load instruction is just a preceding instruction to an arithmetic instruction, for example, or the following, there is a load instruction, and then outcome of the load is required by its immediate the successor instruction, for example. At that time, the forwarding will not help at all, because the load instruction will provide you the output only at the stage 4, only at the after completing the cycle 4. You can see here, suppose this is the instruction sequence. You have a first load instruction, then followed by AND, OR, and so on like this. So here the load instruction will start from here cycle 1, and it will go on, and cycle 5 it completes. And the next instruction, the AND instruction, this AND instruction starts from cycle 2, it will go on. But for AND instruction, the execution stage is in cycle 4. But the load instruction will provide you the output in cycle 5. Will provide you the output in cycle 5. Will provide no, not in cycle 5. So in cycle 5 it will write into that one. Only in the cycle 6 it is available. In cycle 6 only the actual content is available. But here even for forwarding is also the value or the result that is available in the cycle 5. Available from the cycle 5 onwards, the load instruction will provide you the value, the data from the memory that is available in the cycle 5. But here in this AND instruction, we request that value in the cycle 4 itself. So therefore, we cannot forward it, right? Because the value is available from the cycle 5, but the value here is required. The same value is required at cycle 4. So therefore, we don't have that value, so we cannot forward that. So the only way is that actually you need to stop. You need to wait. You need to wait this execution stage till that value is available. Till that value is available. So for that purpose, what you can do, you have to stall the instruction. You have to stall the pipeline at this point. You have to stall the pipeline at this point. That means we have to allow the load to continue. But the AND instruction, when it comes to the execution stage, so we come to know that there will be a problem. There will be a problem. So therefore, we cannot perform the execution and all. We have to wait the execution till the next cycle and all. So it's not to be stalling the pipeline. And for that, we have to see that what can be done and all. That means even though if you have a forwarding techniques and all, but the forwarding techniques may not rescue in all the time, particularly in this case. Like in case of load instruction, the immediate following instruction requires the outcome of a load or the register contents. At that time, you cannot forward and you have to stall the cycle. You have to stall the pipeline for at least for one cycle so that you can able to forward it. So now we'll see that actually here for this, how do we detect that? Because here we need to detect this one. So because for stalling earlier and all we have detected for the forwarding. For forwarding purpose, we have a detection circuitry we have seen, and that will detect the hazards and then it can able to forward the appropriate values. But here you need to detect the hazard, where after you detect the hazard, you will know that actually you have to stall the cycle and all. You have to stall the pipeline. So how do you detect that one? So here this one, you can detect that because the instruction because when you're detecting what here after you detect this one anomaly or like the load instruction followed by arithmetic instruction, then you need to stall. That means you should not perform the execution stage. You cannot perform the execution stage. So it means that whatever the instruction, suppose this arithmetic instruction, right now it's in the instruction like suppose if it is started here and then when it comes to the second stage, the instruction decoding will takes place, right? And then at that time the load instruction is the execution is happening here. The execution of the load is happening over here in the cycle 3, and the arithmetic instruction decoding is taking place over here and all. And then afterwards here, by knowing these things, like we cannot forward. That means the AND instruction cannot be forwarded, cannot be pushed into the execution stage. It has to be stalled. So therefore, if we want to detect this hazard, so you need to compare these two, like the instruction in the instruction decoding will be compared with its previous instruction. The previous instruction will be the execution stage. So these two has to be compared. So that means if we know that the previous instruction is the load instruction, and then the following instruction which requires the which requires the register arguments where the load instruction is supposed to be stored. So in that case, actually here the forwarding cannot be done, and we need to stall the pipeline, particularly this AND instruction at the decoding stage itself. So that if we stall it here, then the AND instruction will be only here. It will not be forwarded at all. Right? So for that, you can see here, like the how to will formulate the condition for detecting this hazard and all. Like load, that means check when the instruction is in the decoding stage. That means if the ALU operand register number of the ID stage is given by this one. This we already know that, because if the instruction here, this is arithmetic instruction, logical or arithmetic instruction. And here at this stage itself, we will come to know that what are these register operands and all. And we also know that what is its type of instruction also, right? So the register operands are known. So the register operands are nothing but this RS and RT, right? And right now they are in the second stage. So therefore, the register names are IFID.RS and IFID.register.RT. So these are the two possible registers where it has to get the values from the following instructions destination register. So this is the condition here. IDEX register RT if it is equal to, because since it is a load register, you can say that since it is a load instruction, the load instruction will put the data into the in the destination register RT, right? In case of load instruction, if you try to recollect, whereas in the arithmetic instructions and all, the destination register is RD. There are three register operands. RS, RT are the source operands, and RD is the destination. Whereas in case of load instruction, the destination register will be RT. RS is the source register which provides the base address, and you have the immediate operand that gives you the offset. So those two together will give you the memory address, and then the contents of a memory will be placed in the register RT. So that's why you can see here the condition will be IDEX dot register RT. It means that this is related to the load instruction, right? IDEX dot RT. If it is equals to the instruction in the second stage, that is in the decoding stage, if one of its operands RS or RT, right? Then that is one thing. And before that, this has to be satisfied. Like the IDEX memory dot read, it means that the instruction in the execution stage where the memory read will be high. The memory read is there. The memory read control signal is high. It means that this is a load instruction, because among all instructions and all, the memory read will be high, or memory read will be set only for the load instruction. For all other instructions, the memory read will be 0, because there is nothing to be fetched from the data, from the data memory. Only the load instruction will fetch that. So therefore, only for load instruction, you can have this one. This memory read will be high. This IDEX memory read will be high. IDEX means because load instruction is now in the execution stage. This will be high. This will ensure that it's a load instruction. Then afterwards, these two conditions will ensure that the load instruction, destination register, whatever it is. So if it is equal to the instruction explicit, this previous instruction, it's a following instruction that is right now in the stage 2. If it has a register arguments, if both are same, then in that case you have the hazard, and then that hazard cannot be solved by the forwarding. So you have to wait for one more cycle. You have to stall. So this way, by using this condition, you can able to check it out whether the load followed by some arithmetic instruction, load followed by any instruction which requires the register argument that is provided by load. If both are like successive, so in that case, the forwarding will not help at all. We need to wait for one more cycle, so that at least the contents of load will be available at the end of memory stage, so that you can able to get it through forwarding. Right? So that way you can able to, by using this condition, we can make sure that the present instruction which is in the decoding stage has to be stalled, and at the same time the instruction following that which is in the fetching stage, that also should not be changed, because the entire thing, the instructions before the load instruction has to be stalled, has to be kept as it is, and then one cycle, empty cycle, or one bubble has to be introduced. It's nothing but one no operation has to be introduced, and that has to be percolated, because you can see here this particular, here we know that there is a this cannot happen and all. So therefore, here at this time itself, the instruction whatever is there here, it has to be here, and it cannot be moved. It cannot be forward to the next stage and all. So it is nothing but these two instructions. The following instructions has to be placed in their respective stages, but they cannot be moved forward. So it is nothing but here what can be done. So therefore, here at this time, so whenever you identify this load hazard, then you need to set the control signals to be 0, all control signals to be 0. So therefore, these control signals will be propagated through the stages, and they will be delivered stage by stage. So therefore, whenever you set the control signal to be 0, so immediately the execution stage, the following execution stage, control signals will be set 0. So it means that there won't be any operation will be performed in the execution stage. because the load is already crossed that one. The load is now in the data memory stage, so it will take care of the data memory. But the instruction which is requires to be go through the execution stage, so that will not go through. That will be just the execution stage will become empty. Cannot happen anything at all. Yeah, sorry. So this way you can able to introduce the stall, and we'll see that how do we do that. So this is the way to detect the stalls. And after the stall is detected, what need to be done is that that means we need to introduce bubble in the execution stage, because the execution stage cannot operate, like, because otherwise the execution stage to operate means the instruction, the decoding stage has to be forwarded, so that cannot be done because you had to stall. So therefore the execution stage has to be stalled, has to be performed no operation under. And then the following stages, the following cycles, the memory has to be not done anything, and then in the next cycle the write back has to be not done anything, so that has to be carried out. So for that, what can be done is that that can be happened through by forcing the control signals in the IDEX register to be 0. If you set the control signals to be 0 during the after you detect the this hazard and all, then the following stages will be successively perform the no operation and all. We'll see that how it happens and all. And the second one is that after the this is for introducing a bubble or introducing a no operation in the EX, then followed by memory, then followed by write back in the successive cycles and all. Because once you are introduced a bubble, once you introduce a one no operation, then the same thing has to be percolated to the following stages, since it is a pipeline, right? And at the same time, whatever the instructions were there in the PC and the instruction decoding stage, they have to be retained. They have to be retained. That means the PC should not be updated. And similarly, the IF stage, the IFID stage, should not fetch the new instruction and all. So both of them should be like no, the content should not be changed. That means those two stages should be in the standstill mode, right? So it means that whatever the instruction that is there in IFID, the same thing has to be decoded, right? Nothing happens and all. And then similarly, the instruction whatever is fetched earlier, the same thing has to be fetched, so that it basically that the register, the pipeline register content should not be updated, should not be changed at all, right? And so we'll see that here. You can see here the way the bubble or the way the stalling will be carried out here and all. You can see the load instruction here, and then here at this point of a time, you can in this cycle, the cycle 3, we'll try to identify that there is a hazard, load hazard and all. So for that purpose, you need to stall. It means that the execution stage of this particular instruction will be make it like empty, will be make it like no operation. And these two stages will not change at all. That means the instructions, whatever one section here, whatever is fetched, it has to be there, and instruction whatever is decoding, it has to be there only. That means these pipeline registers, that is this IFID and the PC, whatever is there. So those contents should remain same. That means those contents should not change. Otherwise, normal pipeline and all these contents will keep on change for every clock tick, right? Now they cannot change. So for that, actually, we'll make the control appropriately that the register contents of these two will not be changed. That means the clock is not enabled in these for these two pipeline registers. The pipeline one is this pipeline register, other will be PC. That is also by default is a pipeline register. So for these two, the content should not be changed. That means the contents are not changed. That means if you don't give a clock, or if the clock is disabled, then automatically these two contents will be whatever is stored, the same thing will be reflected, right? And so that way these two will be there. That means the pipeline, we don't introduce any new instruction. So the pipeline stands still for these two stages. But here we have to introduce no operation. No operation is nothing but here from this stage, after identifying the hazard, you send the control signals to be zeros in all the for all the three stages, because we know that in case of pipeline, we'll derive the control signals in the decoding stage itself. And at this stage, we identify the hazard. So therefore, you derive the control signals for all these stages to be 0. But these control signals will be delivered to these stages at appropriately. That means the control signals, even though we set 0 for all of them, but they will be delivered in the execution stage in the next clock cycle. And they will be delivered after 2 cycles here in the memory stage and after 3 cycles over here and all. So the appropriately whatever the bubble that is raised over here, it's smoothly passed out, and then these instructions will be follow it up. That means here that means here the at this time the no new instruction will be added. That means same instruction will be repeated. At this time you can see that there is a stall here. So therefore you can see here the same instruction is started here. The same instruction again starts from here and all. So therefore there is a delay of one cycle is introduced over here. Right? So this way you can able to stall the pipeline, or you can say that introducing the bubble, nothing but a no operation in certain stages and all. Right? So this way you can handle this. Yeah, this is also this is the same diagram, just to show that actually here how actually these things are happened, the delayed. Not only this instruction, even the following instructions also will be delayed. Like for example, if there is no stall and all, then this R instruction should start from here. Supposed to be start from here because the AND instruction should starting from here. So R should start from immediately after that. But because of this delay, this R is also delayed, or and all the following instructions also will be delayed. So that is just to illustrate that this particular diagram is similar to the previous one, the same as previous one, just to show that all the following instructions also will be delayed, even though they are not in the pipeline. But otherwise, the pipeline runs smoothly without bubble. Then these instructions should be feeded, and they will be advanced by one cycle. But now all of them will be delayed by one more cycle, right? Right. Yeah, this is the, yeah, you can see now here. So this is a data path with the load hazard detection also. Here, this is a forwarding circuit where it used to detect the EX hazard and memory hazards, and then afterwards it will forward to the appropriate multiplexers and also this will be done, right? And now in case of a load hazard, as I mentioned that you hear this hazard detection circuit is there in case of load hazards, and this is a hazard detection circuit where this hazard detection circuit depends on what is that? This is the IDEX memory read. That means the instruction in the execution stage should be a load instruction, and then the contents of the present instruction, the decoding stage, that in the register operands, if they are matching with like whatever the register operand of the destination register operand of the load instruction, then the hazard will be detected. If the hazard is detected, you can see here you have a multiplexer here. The one multiplexer is added because of this hazard circuit. Because if the hazard is not there, then the control signals will be simply pass on. Now, if the hazard is there, then we need to introduce the bubble. So how the bubble is introduced? No operation introduced in the successive stages, and here just placing the zeros to all control signals and all. So therefore, there are two outputs. One is the normal control signals. Other one is that forcing them to be zero. So these two, out of these two inputs, the multiplexer will select one of them. In the normal cases without hazard, this normal output will be selected and it will be passed on. In case of hazard, then the zero output, that means all the values will be placed zero and that will be selected and all. And then these zeros, even though they are set zeros, but all the stages will and these control signals will be delivered only at appropriate times. So that first the bubble is introduced here, then afterwards this bubble will be passed on to here, and it is nothing but here the next stage, the data memory, the bubble is introduced because of this one, and then at the write back stage after that the bubble is introduced, so that because there is no more instruction to execute, so therefore the no operation will be performed. That way, the following instructions where the bubble will be introduced and it will be freed up. And these two instructions, the existing instructions, whatever in the decoding stage and the fetch stage, they will be retained. That means you can say IF write and then PC write and all. So these things will be like by using these control signals to make sure that the PC is not updated. And similarly, the IF also, whatever is there, the same thing will be stored. That means same thing will be retained. Nothing will be updated and all. It means that these two registers are not updated. And then after that it will be updated. Once the bubble is introduced, then you have the required operand is available at a memory stage, then the forwarding can be done. So therefore further instructions will be popped. So one cycle will be stalled, and then during that stalling these two contents, thus these two stages, they remain same. They should not progress at all, right? Yeah. And yeah, you can see that the performance of stalls means actually here Stalls will reduce the performance, as we have seen that, because the pipeline will be like stalled, and some instructions will be take some one additional time slot for its completion, right? And normally in a pipeline, each instruction will take only one time slot for its completion, right? Altogether with respect to overall throughput. But if there is a stall is introduced, then there is one additional time slot will be incurred for the preceding instructions and all. But we need to stall because to perform the correct results and all. Otherwise, if you don't stall, then you can see that that means you will get erroneous results and all. So therefore, to perform the correct operation and all, we need to introduce stalls compulsory at certain places. And you can avoid the stalls maybe by using the compiler appropriately. That means compiler can arrange the code to avoid the hazards and stalls and all. That can be done. But again, this is again there will be issues will be there while based on the logic and other things. And not only that, the compiler should be aware of the pipeline structure and the bottom hardware. So all these things should be completely aware of that, and based on that, it can able to arrange the code so that the hazards and stalls can be minimized. And right. So now we can stop here. Let's take a break for 5 minutes, and then we'll continue this branching hazards and the exceptions and all. Right. So please take a break for 5 minutes. Hello, welcome back. Hello, hello, is it audible? Hello.
Yes, sir.
Yes, sir.
Yeah, right. Okay, good. So, so let's continue the one. So far we covered the data hazards in detail in the different aspects of that forwarding circuitry for that, and detecting the load hazards where we need to introduce the stalls, right? And now we'll just based on that knowledge, that is also required here over in the when you're discussing about branch hazards or control hazards, right? So here you can see in case of branch hazards, control hazards. So this is because mainly you have an ambiguity in fetching the next instruction, right? If the instruction is a branch instruction and the following instruction to be picked up or to be fetched and to be introduced into the pipeline, so there will be an ambiguity. That is whether to fetch the next instruction with a PC plus 4 or whether the instruction will be based on the branch target if the branch is successful. So that's where the you have a dilemma. So with that, you have a problems. You have hazards known to be control hazards and all. And here, if you look at here, suppose for example, this is the sequence of instructions, and assuming that the first instruction is the branch instruction, branch and equal, and then the following instructions are like arithmetic and other instructions are there. So as per this branch instruction, if you look at if the branch is successful, if the branch is successful, then the target instruction will be 72 because here right now the PC is 4. So we'll derive the target for a branch using the based on the PC plus 4 plus the offset. Here offset is 28 bytes and all. It's not words, right? 28 bytes. So therefore 40 plus 4, that is a 44 plus 28, that gives you 72. So if the branch is successful or if a branch is taken, then the instruction to be executed after this, the next instruction to be executed after BUQ will be the load instruction. Suppose the branch is not taken, then you have to go through you have to follow the immediate instruction like and then or so on like this. So this is the sequence of instructions, for example. And as I mentioned, like in normal case, the branch result will be known in the fourth stage because here the branch decoding will be done here, and then here the branch target address are like whatever maybe the branch decision will be calculated or computed here, and then the result is available at the end of this pipeline register. It means that in the fourth stage you will come to know that whether the branch is successful or not. That means what is the actual target address you will come to know here and all, whether it's a PC plus 4 or whether it's a actual target address that will be known here in the fourth stage and all. In the fourth stage. So it means that suppose if the branch is taken, then at the fourth stage you will come to know that the actual PC address, the target address. So therefore, in the following stage, that means at this stage, at the fourth stage, you can see this line. At this point of a time, the PC will be loaded with the target address, and accordingly, the instruction will be fetched from that particular address and all. So if the branch is taken, then the instruction to be followed, the instruction to be fetched will be the load instruction. So that will be realized, that will be known, or that will be done, that will be loaded into the pipeline at this point of a time and all. In the clock cycle 5. But the branch is loaded in the clock cycle 1. And if the branch is success or if the branch is taken, then the next instruction that will be loaded is in the clock cycle 5. It means that during this preceding, during this in between the clock, 3 clock cycles, so the instructions will be feeded will be the immediate instruction because we don't know the branch result, right? So therefore, as per the pipeline principle, the following instructions will be fed into the pipeline, and they are there. They are at the different stages in the pipeline and all. And here at the fourth stage, we'll come to know that there is a branch target. That means the branch is successful. So the instruction to be executed following this branch will be this one from 72. So that will start from here. So in between already these 3 instructions are entered into the pipeline. So they have to be flushed out. They have to be removed from the pipeline, right? And again, you have to restart the pipeline from this instruction, from the load instruction from this point onwards. So if the branch is taken, if the branch is not taken, then there is no issue at all. Then the pipeline will go smoothly and there won't be any disturbance at all. It will go smoothly, right? So that means here the problem is that because the branch is delayed, like because the branch result or the decision will come to know at the fourth stage. So because of that, we have the three instructions that need to be flushed. The three instructions which are already entered into the pipeline, they have to be removed. They have to be cleaned up. The pipeline has to be cleaned up. That is nothing but just removing these three instructions, and then it has to start afresh from the this one by loading the load instruction, by loading the instruction at the 72 address, right? So therefore, one way to overcome this will be like if you can able to perform, if you can come to know the branch target address or branch decision, like before the stages, like it's not in the fourth stage. If you come to know in the second stage itself, for example, somehow by putting additional hardware in the second stage itself, because at the second stage we have the instruction is available and the decoding can be done. We come to know that it's a branch address, and there itself, if you can able to provide some additional circuitry to compute the branch target address as well as the equality branch decision, BEQ or equality can be tested, and after knowing the decision, and here itself we'll come to know the target address and all. That means what I mean to say is that this branch decision, instead of performing at a later stage, if you somehow if you can able to accommodate in the second stage, then at least this penalty or the instructions, number of instructions to be flushed will be reduced. Will be only one instruction to be flushed out, because already in the during the decoding stage, already the following instruction will be accessed from the instruction memory, and it is already ready there. So therefore this has to be removed if at all, if here branch is taken, right? And if the branch is not taken, then there is no issue at all. If a branch is taken, then we have a penalty of only one instruction to be flushed out, like whatever is fetched, whatever is about to fetch, or whatever is fetched and all. So that has to be flushed out, and we had to start from the 72. So that is one option, but for that you need to put hardware or desired circuitry at the stage 2 itself, right? And the other, that means reducing the branch delay, that means moving the hardware to determine the outcome of a branch stage, that is both the target address and the comparator, register comparator, because in case of branch unequal, so there are two register operands will be there, they have to compare that. So comparison is somewhat easier compared to the actual adder and other operations and all. You can, one way to compare is the subtraction. So without subtraction also you can perform a comparator with a few gates with a much easier way, like by using exclusive OR gates. Like for every bit you can perform XOR, and then again we'll do the ORing for all these bits. So that way you can able to perform a comparator job and all. Right? Somehow what it means is that since the comparator is just to check the like two words, 32-bit words, whether they are same or not. So that can be done by in an efficient way with a minimal number of gates also can be done. So somehow if you can able to do it all these tasks in the stage 2, then we can control the number of instructions to be flushed out, or we can control the last to some extent. Otherwise earlier we have the 3 instructions to be flushed out if the branch is successful. And now we have only one instruction to be flushed out, right? So here we can see here this is the the instruction whatever I just mentioned over here and all, like whatever the sequence that is mentioned over here, right? Yeah, that is a different ways of representation, right? Okay, yeah, here for example, if the branch is taken, whatever I mentioned, like if you keep all the circuitry here, you can see here in the stage 2 itself, you can see already hazarding circuit is there for taking care of like load and other things. And not only that, here you can see that here the address calculator, you can see ALU, it just performs the address calculation here. It is a 44 PC plus 4. Earlier it's a 40 PC plus 4 you will get here 44. And this 44 will be added with the 28. So we will get 72 as the target address here. And here there's a comparator. between the two registers, and the outcome of the comparator will dictate that whether the PC has to be loaded with the 72 or with the current one itself, because already PC was ready with the following instruction. PC is ready with the following instruction, that is already 44 is already fetched and it's already ready. 44 is there. That the previous instruction is 40, and now the 44 with that pointing to instruction memory, and the corresponding address will be the data is also fetched, will be fetched in the this cycle and all. But here, depending upon the comparator output, whether the PC has to be loaded with the 72 or with the previous one, that has to be dictated by this comparator and all, right? And therefore we have this multiplexer will be there, and here assuming that actually here, so therefore the 72 also will be ready here, but we had to select actually whether 72 to be taken, or like the same thing like whatever the 44, the next 44 can be carried out, or PC plus 4 has to be entered into this one. So you can see this one, this is the additional circuitry here, the comparator here, equality sign, and here this is the accumulator ALU, which used to perform the this one address calculation. So both of them we are placing over here. So with that you can able to reduce the like the penalty to one cycle and all. So that is happens only if the branch is correct, branch is taken. If the branch is not taken, anyway the previous method also will not introduce any issues at all, right? There won't be any loss at all. But here you can reduce the loss to from 3 cycles to the one cycle for every branch instruction and all. And that depends upon if suppose the branch instructions are more frequent and all, then in that case, assuming that half of them were taken, so correspondingly you have the number of cycles will be, the penalty will be added and all. Suppose for example, if the branch instructions are 20%, out of that, suppose if the 20 of half of them were taken, half of them were not taken, for example. So it means that for 10% of the branch instructions, like 10% of the instructions, overall instructions, because in the overall there are 20%, out of that 50% assume that branch is taken, 50% branch is not taken, just in a statistical sense. So branch is not taken, no issue at all, no penalty, but branch is taken, where for every branch taken, you have one additional cycle is required, right? One additional cycle penalty will be there. So out of 20%, half means 10%. So it means that like the performance will be like earlier, it will be ideal case, it like 1, and now it will be like 1.1 times, or 10% additional clock cycles are required for executing the program and all, right? So that way you can use earlier and all. If it is there, if it is in the fourth stage, then it is nothing but 30%. Like 30% of the times you need to 30% of additional clock cycles are required. Right, so this way you can able to introduce the hardware in the second stage, so that you can able to limit the like penalty and all. And yeah, this is these two figures are corresponds to like here the branch here, then the second stage the calculations are taking place and all, like everything and all, and they are making ready. And suppose if the comparator result is positive, means a branch is taken, at that time these things happen and all. Then the PC will fetch the instruction. PC will give you the address of 72. Then the instruction will be fetched here. Instruction will be corresponds to 72 will be fetched and placed over here, right? And then at that time here you see that. So when the branch is taken, what you need to do, like the PC will be loaded with the new target address, that is 72, right? And then this IFID, because here this contains this branch address, right? So in this branch address, actually here there's nothing to happen and all, because here because the branch instruction already the target address was generated, and there is nothing to do in the branch address because the previous branch address branch unequal. So where we identify that the target the branch is taken, so therefore the new instruction is fetched here, and here at this time where there is nothing to be performed, because the new instruction whatever is fetched, that will be operated in the next cycle. So in this cycle, then after you come to know that the branch is taken, then the new instruction is fetched. But at that time, the second cycle or the second stage, that is decoding stage, nothing need to be performed. Nothing will be performed. So therefore, here you can see that in this stage, you can see the bubble will be introduced over here. The bubble is introduced over here. That is, nothing will be performed. It's nothing but actually here no action will be taken place during this stage and all. So that is indicated here, that is that no registers will be fetched, nothing is there and all. And then it continues. Then the bubble will be percolated to then in the next cycle what happens? Then whatever the fetched instruction, that is a load instruction, that will be passed on to here. And then here at that time the execution stage nothing to do. So the same bubble whatever is there, that will be passed on. That will be percolated through all the further stages and all, right? Right. So it means that it has stalled. That means the previous cycle, whatever the previous instruction, whatever is fetched and all, so that will be stalled. And then the here it will be the bubble is introduced here, and the new instruction is fetched, and the new instruction will be move forwarded. Move forward. Whereas earlier, suppose if the branch is branch is taken, if this result is known in the fourth stage, means then you need to introduce the bubbles in all these things. That means you have to not introduce in bubble, you have to flush out all these instructions. The previous instructions, whatever already there at a different pipeline stages, they need to be flushed. They need to be flushed. They have to be removed. So here flushing means actually here the introducing bubble means by introducing a control signal to be 0, then the no action will be done. But here you have to remove the instructions means here you need to be placed. That means you have to flush. It's nothing but just replacing the contents of the register with all zeros and all. So that way you can able to flush the registers if it is required and all. And that flushing will be controlled if you use the this branching calculation, everything. If you do it in the second stage, then you need to flush only the first stage only, right? Because the instruction whatever is loaded here, so that will be flushed, and the second stage onwards the no op will be generated, and the bubble will be percolated through the stages and the following stages. Yeah, right. And in case of branches, the issue is that actually, as I mentioned, that here you can place the circuitry in the second stage itself, right? In the case of branch, as I mentioned, that the branch calculation and the branch decision, branch target address and the decision will be done in the second stage itself. So if you make a decision at the second stage, right? So there will be again the hazards may happen, because here the second stage it requires the 2 register operands, and these 2 register operands may depend upon the previous instructions, may happen. So in that case, there may be data hazards may occur here and all. And again, to handle this data hazards here, if you push the branch circuitry to stage 2, and again you need to put some additional forwarding and additional hazard circuits are required to handle this case. Because since you are pushing these things, whatever the execution, whatever the decision making process to the stage 2, then appropriately the forwarding circuit, you have to introduce the forwarding and other circuitry also in the stage 2 to take care about this, the dependency of the register operands in the branch instruction to its previous instructions and all, right? So that is one more difficulty will be there. And you can see here that's what data hazards in case of branches and all. Here if you look at here, suppose if there is a branch instruction here and the preceding instructions are some arithmetic instructions, something like this. And now if you look at here, this branch, for execution of this branch, you need to compare these 2 registers 1 and 4. And these registers 1 and 4 are given by are provided by these arithmetic instructions in the write back stage. And these arithmetic instructions, when they are executing, the write back will happen here. The write back will happen at this point. The first add instruction, the write back happens here at this point, and for the second one, the write back happens somewhere here and all. But here the branch instruction to be executed at this point. That means in this clock cycle, the branch branch computation has to be done here. But by that time, write back is not happened for these 2 instructions and all. But the result is available at different pipeline registers and all, the same result. So therefore, you can forward these results to the branch instruction here and all. So for that, what I mean to say is that actually now we are performing the branch in the second stage. So therefore, the forwarding of these things, to perform that, you need to have put appropriate forwarding circuit in the stage 2 itself. In a stage 2 itself. Earlier, we put the forwarding circuit in the stage 3 or in the execution stage. But now, since the execution of this on the branch condition verification, we are performing in the stage 2. So therefore, here in this case, you need to perform the appropriate forwarding circuitry at the stage 2 itself, so that if there are any like hazards or the data hazards in the branching, so that will be taken care and all. That will be taken care. So these will be to some extent, but as I mentioned that all the time you cannot happen. It will not happen at all, right? For example, this branch equal if it is immediately after the add instruction. So at that time, what happens? This is like, for example, just the preceding instruction is somewhat some other instruction where it require the output of where the target where the destination register of this arithmetic instruction is the one of this operand. So at that time, you cannot happen. At that time, you need to stall. You can see that here. Yeah, here if you look at here, suppose there is a load add instruction and then the branch and equal is there. And the branch and equal here you see one of the register arguments are 4 and 1. And here in both the cases 1 you can forward it to some extent because the uh, in case of 1, yeah, in case of 1 also you cannot forward it because the branch you require the branch the register operates in the stage 2 itself, right? So here you can see at the stage 2 you require 1 and 4, right? That 1 and 4 are not available here. The 1 and 4 are available only at this point, like at the end of execution stage of this instruction and at the end of memory stage of this instruction. So therefore you need to stall because at this point of a time, even the desired operand, desired values are not yet generated by the previous instructions. So therefore you cannot operate the branch instruction. So you have to stall, right? And there are places where you have two stalls also required. Suppose there is a load instruction followed by the branch equal, like for example, branch equal preceding that the load instruction is there. So in that case, now we are performing this branch decision in the second stage, but the outcome is available only at the fourth stage. So therefore, again you have to wait. Again you have to wait for 2 cycles and all. That means two stall cycles need to be introduced and all, right? So that way here, yeah, it means that when you push the circuitry to the second stage, all these things has to be taken care. That means you need to see that again, you need to modify the hazard circuitry. That means if the load is there, then the 2 cycles has to be stopped. Or if the arithmetic instruction is just immediately above that, then again 1 stall is required. So all these things has to be taken care when you perform when you place the branching decision at the second stage and all. Right. So that is one way to handle the branches or to reduce the penalty in the branches. The other way is that actually, if you can able to predict the branches, there are static predictions already we have seen, right? That is a branch not taken is nothing but one way of static branch. One way of static branch prediction. It means that always you assume that branch is not taken. So therefore you just you ignore about branch. You just pick up the following instructions, right? So that is one way of static branch. Otherwise, always you the other one is the dynamic branch prediction. It means that you can able to predict the branch at the stage 1 itself possibility, like at the time of instruction fetching itself. If you provide some additional hardware, so with that you can come because the branch instruction and all you can come to know just by knowing the few bits of opcode, right? And then if you know that's a branch instruction, then there itself actually you can have some circuitry to predict that whether this particular instruction will take the branch or not take the branch. If it is not taking the branch, then the PC plus 4 will be taken. If it is taking the branch, assume that in the fetching stage itself, if you come to know that somehow by using some additional hardware, if you can able to predict the branch, like then again predicting branch you can do it. And again after prediction, suppose the predicted address also should be known. So somehow if you can able to provide that particular address also using some cache or some mechanism, for example, then there won't be any wastage at all. There won't be any wastage. That means at the time of fetching itself, branch instruction fetching itself, you are predicting and you are also come to knowing about its prediction address also, the address of the next instruction to be fetched and all. Then you pass that particular address to the PC so that the PC will fetch the branch predicted address and all. But later, when you go to the actual decoding stage, there actual branch calculation is again carried out, right? And there actually, if you somehow, if your prediction is wrong there, then again you have to flush it out, whatever the instruction you have brought in, right? So what it means, dynamic branch prediction means Like you need to predict the branch decision, whether it's a taken or not taken at the fetching stage itself. For that, you need to use some additional circuitry and other things, and not only the prediction, and you have to also provide the branch target address also. So with that, actually, you can provide the target address, then the PC will load the target address, and it will fetch the instruction from the target address. And in the second stage, as per the branch, it will again calculate the actual address based on operands, everything and all. So if you calculate at the time of calculation, if you come to know that somehow whatever the branch taken, suppose you predict that is a branch taken, but there in the when your actual calculation, when you're performing that, you will come to know that the branch is not taken, for example. At that time, whatever the instructions you predicted, whatever the instruction you brought into the pipeline in the first stage, so that has to be flushed out. That has to be flushed out. So, but here the loss or the penalty that depends upon the prediction performance. Suppose if the branch prediction performance is correct, like 80%, 90%, if it is accurate, then like only the 10% of the times your prediction is wrong. And if you can somehow, if you can able to handle the misprediction effectively, then not much loss will be incurred in the overall sense and all. Right, so this is what mean by the dynamic branch prediction. It means that it maintains, actually in the fetching stage itself, it maintains some branch history, like based on the previous branch instruction, whether if this instruction happened previously, whether the branch is taken or not. So that way there will be some table history will be maintained. So based on the history, there will be one bit will be there. That bit will be indicating 1 or 0. If it is a 1 means you go for branch taken. If it is 0 means it means that branch not taken. You go for branch not taken. So that way there will be kind of 1 bit buffer. So with that we'll decide that whether to be branch is taken or not. If it is a taken, then the taken address, the previous address where the branch is taken, that address will be given to the PC. If it is not taken, then anyway PC plus 4 will be there. So that way you can predict the branch dynamically based on its past history and all. And now if you look at here, by using the simple 1 bit buffer by predicting the branches and all, you have what happens is that, suppose for example, assuming that you have a loop, and in the loop, the way the machine instructions will be executed will be the loop decision will be carried out at the end of the loop. That means you have a sequence of instructions. Then at the end of the loop, you check the loop variable, whether the variable reaches the target value or not, right? Suppose, for example, you have 10 iterations, the loop will be carried out, for example. So you started and then you come to know that each time the branch is taken. So with that, the bit will be like set taken. And then when you come to the next time also, then the branch is taken and it keep on goes on. And when you come to the last iteration, as per that, it's a branch taken, you will be taken, but that is a last iteration. And you will come to know that when you compute the branch, you will come to know that that is incorrect. That is incorrect. After you know that if it is incorrect, then you have to set this also. Then you need to set this is incorrect. That means the branch, that 1 bit will be set as incorrect. And you will go for, you will flush that instruction. And again, you will go for from the normal, from the next instruction, whatever it is, and you will continue that. And when you are entering this time, when you are entering this loop again, freshly, again, somewhat later time, at that time, when you're entering this loop, you have the predictor says that the branch not taken, because the last time, as it is the last instruction, you are going by taken, but later you will come to know that's not taken. So therefore you flip the bit, so therefore it's not taken. And even though when you are entering the first time also loop, since it was earlier not taken, you assume that the branch is not taken, so therefore your prediction will be taken as prediction will be provide you the decision as not taken and all. But actually this is the first time when you are entering, but still you are taking that not taken, so you are making a decision as not taken, so you are wrong. So what I mean to say here is that in case of these loop instructions, if you use the simple 1 bit predictor and all, then you are making a wrong, or you are making the prediction wrong twice in every for every time out of for every execution of loop and all. Every execution of loop means, suppose loop is executed 10 times means 8 times you will do correct, but the 2 times you are making wrong. One time is that anyway the last instruction whenever you are executing, at that time you are making mistake because you don't know that whether is it the last iteration or not. So that way you assume that the branch is taken, so you will go wrong. but at that time you are modifying the bit to be not taken. So because of that, when you are coming next time fresh, at that time also for the first time also you are making wrong, because as per the prediction, as per the previous history, it's not taken. So therefore this time also you assume that not taken. So therefore for every loop you are making the mistake, or you're making the misprediction twice and all. So this is because of the simple buffer you are using, the simple hypothesis and all. So you can able to make it better by using a two-bit hypothesis using this particular state diagram. And here the state will change if you have two successive times. If the not taken, then only you will go for not, then only you set the bit to be not taken and all. Likewise, if the taken is there two times, then only you change the state as taken and all. So that way, if you make this kind of two-bit predictor, then the number of predictions go wrong will be one, limited to one, not two. So that way you can improve the performance. Not only that, and there are other techniques, like in case of prediction, not only limited to the local branch history and all. So if you can consider the other branches in the program also, that means taking the global history as well as the local history and taking a correlation between that, and then that will provide you the decision whether the branch to be taken here or not. So that gives you the much better performance and all, but that requires, because you see that all these things are constant in the pipeline. In the in the one cycle, you had to do all these things, right? So therefore, it's a kind of a trade-off and all, whether to use the simpler predictor or like a complex predictor or whatever. And yeah, then calculating a branch address, as I mentioned, that using a cache and other things, you can perform, you can place the branch target address and all. Suppose if you use the dynamic prediction, our aim is of dynamic prediction is that we should not have any loss incurred in the branch execution and all. So we don't get any loss provided the branch prediction is correct. So for that, we'll try to see that the prediction accuracy will be higher and higher and all, right? So again, we want to make it higher and all, then we have a history, more history has to be maintained. And like not only the local branches, the global branches, all of them has to be taken care. So there will be like issue of like trade-off. Right? Yeah, then another way of solving the branches is the delay slots and all. This is similar to the one in the case of data hazards, the way we organize the code to avoid the hazards. Similarly, in case of a branch hazards also, we can able to avoid by properly placing the instructions such that, suppose for example, here add instruction is there, add S1, S2, S3. That means here S2, S3 will be added and the result will be placed in S1 and all. And then following this, we have a branch instruction, right? Here in the branch instruction, we are just checking the S2 value, right? So therefore, there is no problem at all, even though this one, the S2 will be there, one of these source argument. So therefore, since it is not a destination argument, then there is no problem, no hazard at all. So therefore, here in this case, at this time of branch here, so you can keep the above instruction just immediately above arithmetic instruction. This can be placed soon after this one, soon after the branch instruction, and then you assume that branch not taken. Assume that the branch not taken and all. That means avoid this prediction and all. Just go ahead with the normal way of branch execution and all. And since you have taken this instruction, so this instruction doesn't matter. This instruction, whether it executes over here or here and all, it will not influence the correctness of the program and all. So that way here, whatever, suppose here, because by that time in the second, if you look at here, in case of if you make the branch circuitry in the second stage, and if the prediction is wrong, or if the branch is taken, then we need to flush the immediate instruction whatever we entered into the pipeline. But here we need not flush at all, because the immediate instruction whatever you entered into the pipeline, so that has no harm with the whether it's a branch taken or not taken, right? This is a kind of a neutral instruction which is not biased or not reflects any changes with the branching or not branching and all. So therefore, such instructions you can able to place it soon after the branch condition and all. Then anyway, in the one slot or in one time cycle, you will come to know the target address. So with that, you can able to fetch the desired instruction soon after that. So that way you can say that this is before, instruction, and then that can be placed here as a delay slot so that the branching can be carried out. So that the normal execution of branching will be carried out without any flushing or without any loss of cycles and all. And sometimes what happens here, suppose for example, in this case, if S1 equals to, that means if the branch condition to be checked depends on the previous instruction, arithmetic instruction, then it cannot happen. Then you cannot keep it like here in the delay slot and all. So at that time you have to go for some other alternative. So wherever the target is there, that target can be placed, or otherwise the instruction before the target that can be placed. So likewise, you can able to fill up the delay slots based on the requirement and all. And with that also we can avoid the stalls in the branches. Yeah. So then come to the last part, that is exceptions and interrupts. So here the terms exceptions and interrupts both are like used in the literature like interchangeably. Like the earlier they are known to be like mostly the literature they use the interrupts and all. And now actually they made like exceptions by from the MIPS introduction, MIPS instruction, MIPS instruction architecture. They call it as exceptions and all. And some people know some designs or some people they use the interrupts and exceptions for a different reasons, different causes and all. Usually the exceptions they say that if there is any unexpected event happens within a processor or while executing the program, because of the program, if there is some unexpected event happens because of the execution, because of the running of the program and all, due to the program, so those are known to be, those are generated within a processor and all. So they are known to be exceptions and all. And if some program is running and if there is some external inputs or some external requests were there, like from the like a keyboard or from IO device or power failure or some hardware failure or sometime. So those are known to be the those are can be viewed as the interrupts and all. That means they try to interrupt the current execution of a process or a program and all. The exceptions are like viewed as these unexpected events are happening because of the program, because of the running of the current program and all. So that way people define in a different ways and all. Like they are sometimes they are used in a interchangeable way also. Like both the interrupts are called as exceptions and other way also. Right. So basically, whatever it is, this is nothing but an unexpected event when the program is execution and all. That may be due to the program or due to from the outside events also, right? And like this one, like for example, the exception will be like within the CPU it arises and all. Like for example, undefined opcode. That means suppose you fetch an instruction at the decoding stage, you will come to know that the opcode that is there in the 6 bits, that is not the valid one, because opcode 6 bits means there are 64 possible opcodes will be there, and your instruction set may not have all the 64 are valid and all. There may be it may using only 20 or 30, and the remaining 30 may not, is not at all used at all. It may be used for some reserved purpose or something. And suppose when you fetch an instruction and if you come to know that your opcode is not from the valid one, so in that case we don't know how to handle what the instruction is and all. So therefore again it's a problem. You have exception will be raised, and then it will not do anything. Most probably the operating system will throw an error saying that the instruction is not decodable or instruction is not from the instruction set, something like that. Likewise, for arithmetic instructions, overflow may occur. We have seen the arithmetic instructions when you perform a multiplication or when you perform addition, subtraction, sometimes overflow occurs. That means the result will not fit into the 32 bits or whatever. So in that case, the overflow will occur. So there also some action can be taken, like overflow can be ignored and you can continue the program, or sometimes if overflow occurs, then you can terminate the program and showing that as in the form of error. Likewise, the different designers will use the different ways, depending upon the high level languages also. And a system call, it means that sometimes in the execution of a program, it requires the help of an operating system to perform certain activity. And also in that case, the system call is nothing but again, it's a program where this program will be run by the operating system and all. Like for example, somebody you need to enter the input from the keyboard, for example. So in that case, also for accepting the data and all, you have a proper system call has to be enabled. Likewise, suppose when you are accessing for a memory, so a particular instruction, that instruction may not be available in the memory and all, right? On the cache or memory, for example. Then at that time you have to fetch from the disk. So at that time, for fetching the information from the disk and all, you need to have the operating system will take care about those things, not only for different things, right? So we have system calls. It is nothing but the when you are running a program at particular point, you need to have the service from some other resource, and you cannot. The user program don't have access to that. So at that time, the user program will take the help of will request the OS to do that, operating system to do that. So this process of handing over the control from user program to operating system and again back to the user program, so that will be carried out by system calls, and this is again will be like a kind of exceptions and all. And here you see that in all the cases they are similar to the control hazards. In case of control hazards, where the control movement is systematic, that means the user will specify the control where to move, where to go and all, right? Whereas in case of exceptions and other things and all, the user will not do it, because when you're executing a program, suddenly something happens, right? Or otherwise you need to have the service from some other thing. So at that time, the user program can't do that. So therefore, OS or operating system has to do that. So that will be carried out by using some exceptions and all, like interrupts and all. So interrupts are, as I mentioned, in a very broader sense, they say that they are external to the CPU. That means the IO controller, some input device or output device, if it requests or something. So those things, that means the communication between the IO controller and the CPU and all that will be dealt by using interrupts and all, right? So that way, exception and interrupt and all, like the sometimes you can view both of them are similar. Some of them they will sometimes you make a specific definition for exception and interrupt also. So dealing these things will have to be compromised. You need to sacrifice some performance. That's true, right? Because so far we discussed about the pipelining architecture by mentioning about without thinking about these exceptions and interrupts and all, right? So we thought that only our program will be there and we had to run the program. And while running the program, what are the issues in the pipeline and how the data path has to be altered, forwarding circuits and then the hazard circuits and all these things, stalling the pipeline, all these things in view of like only the program sense. We had not we had not included these exceptions into the system and all. And now here we'll try to see that suppose because there are happens in your executing a program, certainly the overflow will occur. Sometimes the code or the instruction whatever you fetched is not the opcode of the regular instruction and all. And sometimes the system call is required. Sometimes the user input, the user will press the keyboard, for example, or sometimes the instruction that whatever you asked for that may not be there in the memory. So that may be there in the secondary memory, for example. So in that case, so all these things we are not thought about. We felt that everything is there in the memory and all. There is no issue at all. So in that case, so what is the data path? What are the controllers? So those things we thought we carried out so far. And now these are the exceptions. And how to handle the exception. So handle the exception is nothing no different from the way we do the branching or like conditional statements and all. So here, what happens when the normal program is executing, at some point of a time, there is some event occurs. That is like unknown event and all. Like for example, when you are performing the arithmetic instruction, the overflow will occur, right? It's up to you that whether you consider that or not. If you don't consider, then you will get a wrong result, end up with a wrong result. Or if you consider that, then you need to take some preventive action, for example. So suppose if you consider that, you know that it is the because now the overflow has occurred. So now you have to mention, then you have to take an appropriate action. So that action will be taken by the operating system where you have some specific code will be there for each of these exception and all. Suppose if a overflow occur, then there is a piece of code where that the control has to go to that particular handler or not to be interrupt handler or exception handler and all. And then that piece of code will be executed. So that piece of code will be that depends whether to again continue the program. Then in that case you do some modifications or replace that register contents to be 0 or whatever, and then you start the execution from that instruction itself. Or otherwise, suppose if you don't want to do that, and then in that case, if you want to terminate the program, then also there is a piece of code that will inform it will display the saying that the program will be terminated because of this particular exception number and because of these causes and all. Then the program will be terminated and the next program will be executed and all. So that way, whenever the exception occurs, then immediately the control will be shifted to a place where the exception routine or exception service routine, or you can say that interrupt service routine. So that has to be carried out. That has to be run. And that interrupt service routine, that depends upon the way you handle the interrupts and all, whether to terminate the program or whether to run the program, the remaining part of the program with modifications of the register contents or whatever. So that is up to you, right? So for handling these exceptions and all, the MIPS exceptions are managed by there is another processor will be there along with the normal CPU, known to be like a control processor, system control processor that used to handle these exceptions and all. And it provides certain registers and these service routine provides some registers and other information, like it provides a register known to be EPC, known to be exception program counter. So this is basically, suppose when you are executing a particular instruction, like at that time your exception has occurred, like overflow has been occurred, right? So that time, based on that, based on the designer and all, you need to rerun the program starting from this instruction itself after you perform the instruction handler and all, right? So for that purpose, you need to again, because when whether the exception occurs at that time, immediately control will be taken by the operating system. Control will be given to the operating system. Then operating system will execute the corresponding routine, corresponding service routine for this exception and all. And after that, again, it has to come back to the instruction where the interrupt, where this exception has been occurred. So to come back to the instruction where the exception has occurred, so for that purpose, the address of that particular instruction where the cause, where it's a cause for the interrupt, where the cause for the exception. So that address will be placed in a register known to be EPC. That's known to be exception program counter and all. So this is just to return after performing the interrupt service routine or exception handler routine. If after running that one, the last part, the last instruction will be like return to a register where the register contains this particular address, the address of the instruction where the interrupt has been occurred and all. And along with that, there is one more register known to be the like cause register and all, where in this cause register there is a provision to specify the cause of this interruption, the cause of this interrupt or exception and all, whether this interrupt exception is due to the overflow or whether the exception is due to the wrong opcode or like undefined opcode, or whether the exception is due to the system call or whether the exception is due to some other thing. So that cause will be noted or cause will be placed, will be marked in this cause register and all, right? And then these two registers will be there, and then afterwards, whenever the exception occurs, and then immediately in case of MIPS, the program counter address of the present instruction, the instruction which caused the interrupt, which caused the exception, that is loaded into EPC, and the cause will be mentioned, loaded here, properly marked here, updated here. Then then the control will then the control will control means then the PC will be loaded with this handler and all, with this address at this place where the operating system routine will be there, that used to check the cause register, what is the cause for this exception, and then based on that the corresponding cause routine, that is nothing but the exception routine, exception service routine, so that will be executed and all. And upon completion of that execution, then again it will come back to the instruction where it is interrupted, that is due to that is given by the EPC and all. So that way the exceptions will be handled and all. We'll see that how they are. And there is another way. This is one way, like keeping the EPC in one register and the cause register will be updated. Then afterwards, it will go to the a single place where the operating system will take a control, and the operating system will observe this cause register. So with that, it will come to know that what is the cause, and then it will execute the corresponding routine and again come back. Right? That is the way it happens in one of the methods and all. The other alternative will be that using a vector interrupts and all. The vector interrupts, the way all these exceptions, suppose you have 10 exceptions are there, all these 10 exception routines are placed starting from a particular address, something like that. This is the hexadecimal notation of address C000, and then the like this is undefined opcode where starts from this one, where the overflow will start from this one, where some other exception will start from this. So likewise, all these the interrupt subroutines or like exception routines, they will be placed starting from these at some specific addresses and all, and they are in the vector form. That means all these routines, if you see that, they are like they are separated by constant the same address space and same address range, right? So that way, if you have a 10 means then 20, 40, 60, and so on like that. So now in case of vector interrupts, whenever the interrupt occurs or whenever the exception occurs, based on the type of the interrupt, immediately the control will go to the corresponding address and all. Suppose there are a sequence of addresses, that's why there will be vectored addresses or vectored interrupts and all. Suppose if the cause is overflow, then we know that because at when the time of execution overflow occurs, so that will ensure that it's a overflow, and with that immediately the PC will be loaded with the corresponding overload routine, overload exception routine and all. So that way it will be routine that. So then when this when the control goes to here, at that time the operating system starts running. Then by knowing this address, the operating system will come to know about the what is the cause for the exception, and that cause will be marked in the cause register and all. So that way there are two ways to handle the exceptions. One is known to be using vector interrupts, where whenever the interrupt occurs or whenever the exception occurs, immediately the control will be reaches to a corresponding address where the corresponding where the respective exception handler will be there, right? And then when the operating system come to because control goes to there and the control will be given to the operating system, then the operating system will come to know about, based on the starting address of that, it will come to know about what is the cause for that, and cause will be properly registered into the at appropriate place at the register center. And here, when the exception occurs, what happens here? That means the control is moved to the some other place, right? When the control is moved to the some other place, and then at that time, because the exception may occurs in the decoding stage. Suppose if the undefined opcode where the exception occurs in the decoding stage, and whereas arithmetic instructions, the exception occurs in the execution stage. So at a different stages, the exception may occur. So for example, in case of arithmetic instruction, exception occurs at execution stage. So till that you don't aware of that. So therefore, there are two more instructions that are preceding to or successive to that. They are entered into the pipeline. And when the exception occurs, then immediately whatever the instructions before this particular instruction, so they will be flushed out. And then by knowing this exception, the corresponding exception routine has to be start. It means the starting address of that has to be placed into the PC and that has to be run, right? So that way, in that whatever the previous stages instructions are there, so they need to be flushed out. They need to be flushed out, and then this execution stage, whatever is there, so that will be. But the current instruction should not be disturbed, because whatever the contents are there, those contents has to be saved, and with that contents later for the analysis of this exception and other things may be required when you're performing an exception service routine. So therefore, the current instruction contents will be preserved, but the preceding instructions, whatever is there in the pipeline, so they need to be flushed out, right? And then the following instructions, then anyway afterwards you can whatever the current instruction, whatever, so that also has to be like no operation has to be placed, and then it will be then anyway the service routine will be there, that will be starts continuing, right? And yeah, this is the handler as I already mentioned here, like yeah, read the cause and transfer to the relevant handler. There are two ways. One is that first the operating system will see the cause and then it will go to the corresponding handler. It will do that. That is the normal way of MIPS will do. Whereas some other option is the other ways of doing handling the exceptions is that using a vector interrupt where all these exception routines are there at a fixed addresses and all, and then wherever the exception occurs, immediately the control will be transferred to that particular address, and there those instructions will be handled by only operating system. Then the operating system, by knowing the starting address, it will come to know the cause, and the cause will be registered or be saved at some place, right? And yeah, these things, like whether the instruction can be restart or otherwise you can terminate the program also. That depends upon the way you handle the exceptions and all. Some exceptions and all, it will simply terminate the program and then it will throw the message and all. And some exceptions where it can, for example, if the exception is like a wrong code, wrong operation code, then nothing to be done. So in that case, you display the message as this one, and then you terminate the program, right? And some other things like arithmetic instructions and other things and all, where if that result is not that important, so in that case actually you can overlook, you can display the message, and or otherwise you can restart the instruction from the save point and all, right? So that way the exceptions can be handled. And so these are the, like you can say, the pipeline or control diagrams for the exceptions, because in the exceptions you can see that there is ID flush and EX flush. That is, the exception may occur in the decoding stage or exception may occur in the execution stage and all. So if the exception is occur in the like for example in the decoding stage, for example, then after that the following instruction, that in the following cycles and all, nothing to happen, like no operation has to be introduced. So therefore here you can see that this particular OR gate. So with that OR gate, actually this OR gate takes the two inputs. One is the normal hazards response to that, and this is for exceptions also. It will take ID flush. Suppose if the exception is detected in ID, then you need to flush it out. So therefore this input will be given. In either case, the multiplexer will introduce the 0 in all control bits and all, so that the no operation or bubble will be introduced later on. And at the same time, if the exception occurs, the preceding stages has to be flushed out. That means the instructions, whatever are the contents, whatever is there in the previous registers, they should be flushed out. So that will be done by using, suppose for example, IF flush is there. So with that, whatever the instruction that is there here, that will be flushed out. So likewise, the preceding instructions, whatever is there, that will be flushed out, and the no op or like a bubble will be introduced in the following stages and all. So that and then at the same time, for example, here you can say exception handler, that is 800180. So that will be loaded. That is loaded and all. And at that time, after loading that one, then the operating system starts execution of the instructions, and then it will identify the cause, and it will again load the corresponding routine, and it will be executed and all. You can see that this is the more detailed one you can able to see here. Suppose add instruction here, suppose exception occurs and all, then what happens and all. If the exception occurs here, and here corresponding, you can see here this thing will be exception is occurred here, right? And afterwards here you can see that these things, the zeros will be, because exception is occurred here, the control signals whatever here afterwards, you have to place the no operation and all, like you have to place the bubbles here after the from this point onwards. So therefore you can see that because exception occurs in this stage, so therefore here the EX flush will be used to feed the zeros to the control signals. If the exception occurs here, the ID flush will place the zeros into the control lines. So this is just before exception occurs. And suppose if after exception occurs, you can see here the bubble will be there placed here in the corresponding places, and the instruction will be flushed out, and the desired instruction from the service routine will be fetched, like SW, the stored word. This is corresponds to the instruction starting from the instruction handler and all. So that way it's just like the some other place where the control has to go, the instructions has to be executed. So this way the instructions can be like the exceptions can be introduced or can be inserted into the normal processor along with the normal regular programs execution and all. Yeah, this is anyway the concluding remarks, whatever. So with that, we can stop the lecture here. So the next class will start the memory and the related things. So we'll stop here. So if you have any questions and all, in the next class at the beginning, we'll handle that. Yeah, let me. Yeah, sorry, actually now it's it's 12 o'clock. So please leave if you have classes later. Yeah, now let me stop the recording.